Vorticity is an important concept in fluid mechanics. Vorticity is observed as the motion of a fluid element in circular streamlines. It is a vector quantity that is proportional to the angular momentum of a fluid element and has a precise mathematical definition. It can be modeled as the curl of the velocity vector.
As seen here, I have written a mathematical definition for vorticity. From this definition, we can derive the vorticity transport equation. The first term represents the local time rate of change of vorticity. The second term represents the advection of vorticity by the bulk flow. The third term represents the change of vorticity by tilting and stretching of the vortex lines, and the last term represents the diffusion of vorticity due to viscous effects.
There are two basic types of vortex flows: solid body rotation and the irrotational vortex. For solid body rotation, the vorticity of an element is everywhere equal to omega. In contrast, the vorticity of irrotational flow is equal to 0 everywhere except at the origin, where it is infinite. Vortex lines, also called vortex filaments, are curves in a fluid that are everywhere tangent to the vorticity vector, which gives the direction of local vorticity. Similar to the effect of a streamline, a vortex line is related to vorticity vector. Just as streamlines bound a stream tube, a group of vortex lines bound a vortex tube.
Now, consider an infinite incompressible media that is at a steady, uniform flow in the x direction with no applied pressure gradient and no viscous effects. If we were to spontaneously generate a vortex ring that is very large, and consider a very small portion of that vortex ring, it would appear as a vertical vortex tube that rotates at a constant speed and would travel through the media in the x direction forever. Now, if we add viscous effects to the media, we can see that according to the vorticity transport equation, there will be diffusion of the vortex ring.
The aim of this experiment is to model a vortex tube in a water channel. The water channel used in this experiment has a total capacity of 40 gallons, and we tested 3 different flow speeds. To begin our experiment, we started with a flow speed of 30 millimeters per second, as seen here. A vortex is generated by inserting a plate in the flow that is parallel to the free stream velocity. The plate starts at one of the walls and is then slid across the bottom of the channel, which will create a pressure differential in the flow. This pressure differential is what causes the vortex to form. According to the dissipation length equation derived in the report for this project, we anticipate the vortex to dissipate due to viscous effects after approximately 11 inches. In the experiment, we observed that the vortex dissipates at a little after 8 inches. Next, we reduce the flow speed to 22 millimeters per second. From the previous experiment, we know that using our dissipation length equation, we can calculate the dissipation length for a vortex. In this case, the dissipation length is calculated to be approximately 8 inches. The observed dissipation is around 7 inches. And finally, we reduce the flow speed to 18 millimeters per second. This flow is calculated to have a dissipation length of approximately 5.7 inches. The observed dissipation length is just over 9 inches. With the conclusion of this experiment, it is important to consider the Helmholtz theorems of vorticity, which state: 1. Vortex lines move with the fluid. 2. The strength of a vortex tube, which equals circulation, is constant along its length. 3. A vortex tube cannot end within the fluid. It must either end at a solid boundary or form a closed loop called a vortex loop. 4. Strength of the vortex tube remains constant in time. At each of the flow speeds, we observed high dissipation rates for our vortex tubes. We believe that the rapid dissipation of the vortex tubes in our experiment was due to the relatively small geometry of the water channel, which allowed the channel walls and floor to interfere with the propagation of the vortex tube.